I'm Tyler, and I'm going to talk a little bit about some natural language processing approaches to vectorizing text, to algorithms, and how to do some of these things in Python within Jupyter notebooks. So the audience I have in mind for this video are programmers who know very high level what machine learning is, but otherwise actually don't have a lot of background in machine learning. There will be just a tiny bit of math, but I don't plan to go very much in depth in the math. This is more about a conceptual introduction to two specific topics. I'm going to talk about vectorizing text and specifically Tf-Idf vectorization, which is a way to do it that's a little bit more sophisticated than counting words. And then I will also talk about turning that into a way to automatically label documents yes or no within a certain category that you define with training data. So the specific kind of classifier that I will talk about is called logistic regression. So I'll try to explain in some detail exactly what logistic regression is, conceptually, how you can sort of think about the way that it works, and a little bit of the math behind it. And I'll also give an sklearn example of doing all of these things towards the end of the video. So, all right, let's get into it. Just to recap, the topics here are going to be vectorization of text. What that means is that we are taking a string and we are going to return a numerical vector that somehow represents that string. In particular, Tf-Idf vectorization. There are many ways to vectorize text, but Tf-Idf is a classic way. It often works well. It's good to know about. And then I'll also talk about logistic regression, which is a particular way to classify. Because we're starting with text, I'll say we're going to classify text documents based on training documents. All right, so let's get a little bit more into this. So first, very high level, what is the general process of vectorizing documents and training and using a classifier in production? So let's say that we have a lot of text data. Somehow we're going to vectorize that text data. So we could say she ate some pizza. This is a happy story. So most machine learning models think in terms of numbers, so somehow we have to vectorize this. And let's say, I'm not going to explain this, I'm just making this up. Later I'll explain the ways that this actually happens. Just as an example, let's say somehow a vectorizer converted this string into this vector. Okay, and then as long as you have a consistent way to vectorize, which means that somehow the coordinates of your vectors mean the same kind of thing that they do across all documents. So if there was another document, let's say it was good, because the pizza was good. However we vectorize this other document has to preserve the meaning of the coordinates so that the coordinates sort of can be compared mathematically. And that's a very vague and general statement. So as we get into Tf-Idf vectorization, that will make a little bit more sense. Okay. So let's suppose we have vectorized a large set of documents and that we know some labels. So let's say there's a huge list of 50 million documents that we want to classify. And we have a list of about 10,000 that we already know about. So what we're going to do, let's say we're classifying web pages. That's a very common example. So then somehow we'll have a matrix here. And what I'm doing, I'm writing text here. What I mean is the vectorized text of each of these web pages is in that matrix. So each of these rows corresponds to one of these vectors. And then back here, there will be some kind of labels. So let me give you a concrete example so you can have a sense of what these labels might look like. These are supposed to be ones and zeros here. One example might be, well, later I'm going to give an example with news articles. And there's a recent news story about Joe Biden giving a speech, I think in Philadelphia. And so we could build a classifier that, let's say we're part of Google News, for example. We could build a classifier such that given the 100,000 news articles that came out today on the web, which of those are about this event that Joe Biden gave this speech in Philadelphia? So we'll have some training examples where we have 10 documents, for example, that we know because a human labeled them is about that topic, and then we want to find the rest with a trained classifier. All right. So what is the process that we go through to make sure to train the classifier and to make sure that the classifier is actually doing a good job? So generally, when you have labeled data and you're solving a new machine learning problem, you start by shuffling and splitting the data. And the reason you want to shuffle the data is that sometimes you accidentally have some kind of an order in the original data set. So the shuffle helps make sure that you're not accidentally biasing the training data in a separate way from data that you'll later look at to test how well the machine learning model is actually doing. So after the shuffle and the split, we're going to have two chunks of text and labels. So it's the same type of data that we had on the left. The only difference is that it's been randomly put in a different order, and we've got two different pieces of it. So the top piece here will be the training data, and then the bottom piece is going to be our test data. In practice, when you are actually building your classifier, when you're actually choosing the weights or the parameters within that classifier, you never look at your test data. The reason for this is that if you were to look at your test data while you were training, you would you could give the model the opportunity to just memorize the values in all of your data, and then you wouldn't really know what to expect when the classifier saw completely new data that it had never encountered before. So you hold out that test data, and then after you're done training your model, you check to see what percentage of the time your model is correct on that test data. So here's the general workflow. So basically, there's going to be two steps. One, we have training time. And at training time, that training data is going to go into some kind of a training algorithm. Now, every time you have a different kind of machine learning model, you will have a different training algorithm. So logistic regression will have its own training algorithm. Deep learning models tend to use a process known as backpropagation. If you were using like a linear regression model as another kind of model, then there are some very classic and well-established ways of training such a model. Some models use iterative methods. Some models have closed-form solutions, such as logistic regression with least squares. We don't have to get into that. So training time you just look at your training data, you get the trained model out, and then when you're ready to test it, this is at test time, we're going to take in that test data that we held out, and then we're also going to use the trained model, the same one that I just drew above. Those are sort of the inputs to a prediction algorithm. So really there's kind of two ways to use a classifier, or sort of to work with it, I'll say. One way is to actually change it by training it, and the other way is sort of more read-only, and that's when you actually predict on new data what you think the output label should be. So when you get your predictions out, the predicted value is often going to be a confidence score. This is, I'm speaking in the case of a yes or no decision, which is called binary classification. Let me write that down. So binary classification is a certain type of machine learning problem where we get yes/no answers. Like, is this news article about Joe Biden? That's a yes/no question. Sometimes there are multi-class classification problems where there are multiple answers instead of just two. And there are whole different areas of machine learning, like unsupervised learning, where we want to say cluster data, and there's no labels given, it's just data. We want to say, like, this data is like itself, and this group is different from the first group, but it's still like itself. That's clustering. There's reinforcement learning, where we sort of teach an agent to play board games or video games or fly like a remote-controlled helicopter, for example, or self-driving cars would be another use case of reinforcement learning, where there is our sequence of actions and reactions that lead to good long-term behavior, essentially. All right, so what do we get out of the prediction algorithm? Essentially, for most models, we have confidence scores, and those confidence scores are going to be per input. So let's say there are, let's pretend like there are 5 test documents. Then if we, in batch, get a prediction for each of them, then we'll get a length 5 vector of confidence scores out. And then the actual predictions here will just be rounded integers. So it'll be 1, 1, 0, 0, 0 as our predicted outputs based on the confidence scores I've given here. So those confidence scores are from 0 to 1, and 0.5 is a natural cutoff point. You can actually choose different cutoff points, but 0.5 is a default for logistic regression. And once you get those predictions, you can measure accuracy. So I'm going to copy this. Nope. All right, so there's going to be some kind of a ground truth value to our test data. So this was part of our test data. All right, and let's say the ground truth was something like this. Okay, so then the percentage that we got correct in this case is going to be, I believe, 3 out of 5. Right? So that means that we got 60% correct. Not that good, actually. You know, if I make up examples, I might as well pretend I'm doing a better job, right? This is called the accuracy. So the accuracy is the same as the percentage correct out of all of your test data. All right? And I'm going to talk about 2 other key metrics in terms of measuring how well we're doing. Okay, so I'll also talk about precision. All right? So the precision of a classifier is equal to the percent of predicted yeses that are correct. I'll write that down. So I'll give you some examples where you care about precision. You always want it to be 100%, but sometimes there's a trade-off between precision and recall, which is it's sort of a business decision in terms of which one you want to maximize. You may find one is more important than the other, right? So it's just good to know about these metrics and to be able to think about them for business purposes more. Recall is going to be the percent of, let's see, the percent of true yeses, I'll say. True yeses that were predicted yeses. Say that were also predicted yes. All right. So in the Joe Biden news article example, let's say we predicted 30 articles would be about Joe Biden, and in truth, only 20 of them actually were. Then our precision is about 2/3. Now let's say that there were a total of 40 articles in the entire set that were actually about Joe Biden, and we said we only correctly noticed 20 of them, even though we predicted 30 yeses. Remember, only 20 were correct. Then our recall is 50% because we only got 20 of those articles correctly out of the 40 that existed. So precision and recall are two different numbers. They could be highly disparate. One could be great, the other could be terrible, or they could be both good, they could both be bad. They're not completely independent, but just mathematically speaking, any combination is possible. So let's give an example where you want one or the other. You're the hedge fund, and you have a great reward if a yes is correct. A yes means I'm going to act on this idea. And there's a great punishment if a yes is incorrect. Now, if you miss opportunities, it's a little painful because, oh, I could have been making more money, but you don't actually pay that money directly. It's an opportunity cost, all right? So in the hedge fund example, you would want the precision to be very high, and then the recall is less important. Now, another example is diagnosing a potentially terminal but curable disease. So if you are using an algorithm as part of a diagnosis pipeline, you definitely want the recall to be high. And if the precision is low, let's say the precision is only 60%, that means when you diagnose this disease, 40% of the time you're actually wrong. Well, the cost for the patient in that case is probably some trauma because they're worried, but they live, right? Now, if your recall is very high, let's say 99% of the time you catch this disease, that's great. That means almost all the time, if someone has that disease, you will notice it and treat it, which is good. If your recall was only 50% for this diagnosis, half the time someone had this disease, you would miss it, right? So the medical diagnosis case, you want the recall to be high, and then in the hedge fund case, you want the precision to be high. Often, so in my experience as a machine learning consultant, often businesses have customer-facing decisions. And when they have customer-facing decisions, it's very common that the precision needs to be higher. All right? So you kind of have to look at what are the consequences if one of these is low. And usually there are worse consequences if one or the other is low. Okay, so that's very high level how we can measure these things. And actually, I'll get into a precision recall curve here. So let's say we have some data. So I'm going to make up some data. Let's say this is equal, let me use different colors here. A blue circle is equal to a yes data point. So this would be, for example, a news article that is genuinely about Joe Biden. And then I'll use, I won't go red and blue because it's too political. I don't want to get too political. So we'll put green here as a no data point. And you'll see where I'm headed with this. What I'm going to do is list the test data in order of confidence score that's output by the model. Okay, so let's say it looks like this. So the low confidence scores are going to be on the left, and the high confidence scores are going to be on the right. And towards the left, we're going to tend to have more green because the classifier is doing a fairly decent job. And then we'll make a few mistakes. And then we'll put in some of these yeses here. All right. So if you think about it, now what I can do is I can choose a cutoff. So let's say I choose, let me use different colors here. Let's say I choose this magenta cutoff. If I choose this cutoff and say everything here is a yes, then my precision is going to be, let's see, it's going to be 5 out of 9. Okay, so that's about 55%. And then my recall is going to be 5 out of 6, which is actually pretty good. I think it's like 84-ish%. Okay, now what I could do if I wanted higher precision is I could increase the cutoff threshold. So let me use like a bright green here. Let's say I choose a different cutoff. And what I'm going to do now is I'm going to say everything above this cutoff, it means yes. Let me throw in some confidence numbers so you actually can see what I'm talking about. So this could have a confidence score like 0.1, 0.12, 0.2, 0.22, 0.3, 0.35, and then this will have a confidence score of 0.9. So you can kind of see where I'm going here. So the magenta cutoff was about, let's say it was 0.32, and then the bright green cutoff is going to be 0.52. Okay, so the precision with the green cutoff is going to be 4 out of, let's see if I get this right, 6, right, which is going to be about 68-ish, I think. Wait, yeah, 60. It's 2/3. 67. And then the recall is going to be 4 out of, oh, it's the same thing. It's actually going to be 67 as well. That doesn't always happen, but in this case it did. So you can see that by increasing the cutoff, the precision has gone up and the recall has gone down. And that's common, but the only thing that's guaranteed as your cutoff increases is that your recall will go down. The precision can actually go up or down. So let's draw a nice summary. One thing you may have anticipated is that we are headed towards the ability to graph these different ratios. So what I can do is I can take this point. So let me draw a graph here with precision on one axis and recall on the other axis. And what I can do is I can try to map this point. Precision is about 55-ish. Recall is about 84-ish. So this is one of the points on this graph. And then looking at these values, 67, 67, it's going to be like here, here. So it's going to be about here. And then if I were to actually plot all of the points here, I'd have 1 point for every possible cutoff. Now I'm going to just make up the actual curve here. I don't know what it will look like, but generally it kind of goes down and to the right. And ideally, let's say this is 1.0 and this is 1.0, the ideal graph would actually fill up completely this whole rectangle. I mean, if the aspect ratios were equal, it would be a square. but I didn't draw the aspect ratio equal. And often what people do, people often like to have a single number to look at. So sometimes they look at this area, the area under this curve. Now the term AUC stands for area under the curve. Now, area under the curve actually is not usually applied for this specific type of plot. And it's a little tricky. Area under the curve usually is applied to what are called ROC curves, which are just a little bit different. An ROC curve looks at, one way to look at it is, I think it's true positive versus true negative rates, which is very similar, but it's not exactly the same. So I don't actually want to define ROC curves right now. ROC stands for receiver operating characteristic. And that actually comes from, if I remember correctly, I think it's a term that came out of World War II, possibly. I think that it had to do with trying to identify telegraph operators. The name ROC is such a weird term in machine learning. Receiver operating characteristic. That is not what I'm talking about. I'm talking about precision recall curve. And then when you do look at this area here, typically the area here is actually called the average precision. Because if you think about it, if you look at all the possible precision values on this curve, you're basically weighting them by the amount of the recall that they account for on this graph. So in a sense, it is kind of like the average precision if you look at the area under the curve in this way. In any case, the average precision is a single number that you can optimize. Whenever you have one number, you can always optimize it completely. You can globally maximize it. Whenever you have two numbers, you have to have like a human-made decision to figure out what you want to prioritize. All right, so that was an intro to precision recall. Okay, I'm going to talk briefly about overfitting. So overfitting is a particular type of common problem in machine learning, which can occur for many reasons. The high-level thought is that overfitting is like memorizing your training data. I think that's the best intuition. The problem with memorizing the training data is that if you think of your classifier as a student, your student might be very proud of themselves because on the examples you've shown them and on the test that they took on that training data, they did great. They're convinced that they know everything. But in truth, let's say they're learning multiplication and they've just memorized the table up through 10 times 10. As soon as you give them 11 times 10, they might fall over and not know what to do, right? And so this is a type of problem that can happen. For example, if you have only 2 or 3 examples of training data, let's say you want to classify apples versus limes, right? Let's say you give it 3 red apples, 2 limes, and then the classifier says, okay, everything green is a lime. And if it's not green, it's an apple. And then you give it a green apple, that classifier will fall over because it has basically latched onto a pattern that existed legitimately in the training data, but did not exist in all of the data in the rest of the world. So I'd like to show you a common heuristic for knowing that you're in this situation, that you have overfit your data. So one way to look at this is to plot both your training metric, like your training usually accuracy, as well as your test accuracy. So let's say here, this is your training accuracy. It's about 0.9. All right, and then if your test accuracy is not too far away, typically your test accuracy will be lower because this is data that it's never seen before. It's like when you take the final at the end of your class and there's a question that you feel just a little unfair because it wasn't really covered in the class. But that's just life for poor little classifiers. Now let's say your training accuracy is 0.9 and your test accuracy is 0.45. So this is kind of, I'm going to label this as typical, and then I'm going to label this as overfit. There is something called underfit, which is usually you don't have to worry about it because it's obvious. I'll mention underfit at the end briefly. Overfit is the memorization case where there's a huge gap here between the test accuracy and the training accuracy. And when you have that situation, there are many things you can do. Often you can try to get more data. That is the single best and basically universal way to improve your machine learning performance. But there are a lot of other ways. So for example, if you are using a non-deep network, you could try to use regularization. Regularization basically means you add a term to your loss function, which I didn't really define yet. I'm going to write down loss function. It's the same as a cost function. And I will define that in the future, but for now maybe have a mental placeholder that that is something you can mess with to try to fight overfitting. If you have a deep network, there is a technique specific to neural networks called dropout, which basically tries to suppress overdependence on a relatively small number of features, which is akin to memorization for machine learning models. I think I might be forgetting one or two here. Regularization can be applied to neural networks as well. There are other techniques here, such as data augmentation. Data augmentation means that you start with your labeled data and you use usually domain-specific techniques to sort of drastically increase the size of your training data. So for example, if you have images, what you can do is provide slightly shifted, slightly rotated, or slightly cropped versions of those images, or perhaps, for example, invert the colors of the images if you think that's a reasonable thing to do depending on the data and the problem at hand. Okay, another technique that you can try is to try to decrease the sophistication, sometimes called the capacity, of your model. All right, and so one way to think about this is, if you gave a little kid a pattern to try to understand, they would probably come up with a rule that was reasonable, and then if you gave them an exception to the rule that they came up with because they had the wrong rule, then they would probably just tack it on, accept this, accept that, so you end up with this long chain of if-else things, or sort of like let's call it a toddler-made decision tree, where they go through and do their own version of 20 questions on your data, right? That kind of a model will tend to overfit simply because the reason I'm using the word toddler here is that kids tend to not want to completely throw out their first hypothesis if they can. Or this is like one model of kid. Maybe kids are smarter than I'm giving them credit for, but the idea is that if you come up with a model that feels inelegant and full of ad hoc rules, like a European board game with a 40-page instruction booklet, that kind of inelegance tends to correlate with a tendency to overfit. And so when I say decrease the sophistication of the model, what I mean is try to go for Occam's razor. Try to look for simple patterns, because simple patterns tend to generalize better. Okay, so that's a little bit about overfitting. All right, let's talk about Tf-Idf vectorization. Tf-Idf, usually lowercase. I don't really particularly know why. It stands for term frequency inverse document frequency. And that's basically, in English, spelled out the formula Tf, term frequency, divided by Df. So the name of it incorporates the formula. I like that naming scheme. personally. And actually what we're going to do first is we'll talk about tokenization. Because whenever you have text, you need to break it down into your individual terms as a sort of a list of somehow canonicalized or standardized terms. They're often called tokens, and the process of getting them is called tokenization. So the input here is some kind of an arbitrary string which contains natural language. And then we're going to map that to a list of what are called tokens. And tokens don't have to be words. They could be phrases. They could be subwords. They could include some punctuation if you want. I'm going to exclude punctuation. So here's the process I'm going to talk about. And it's not like there is one standard tokenization method. Rather, there are a lot of techniques, and on a case-by-case basis, typically people will choose the tokenization that works for them. For example, if you're working with Twitter data, you probably want to keep around your hashtags because those are very interesting. Whereas if you are working with someone's PhD dissertation that's not about Twitter, then the hash symbol is less likely to be important, and you could probably throw it out with most of the other punctuation. So, and sometimes you want to keep punctuation or provide special case treatment of punctuation. I'm going to lowercase the entire string. I'm going to remove all punctuation, treating it as white space, which isn't perfect, but it is simple and very often will do what you want. Right, treat as white space. The alternative to treating it as white space would be to actually just delete it and replace it with empty string. But then, for example, if you have someone with periods between words, let's say they forgot to write a space character after a dot, or they're using some kind of acronym that includes periods, like what would be an example of this? Well, maybe they wrote like dr.s. Then dr by itself as a word is almost always going to mean doctor. And so you want that identification to hold true across all your documents. So if it's doctor's orders and they use the period apostrophe, you kind of want to treat that as dr, the token dr again, instead of drs as a separate token. Okay, so that was a made-up example. There are probably better examples, or like, oh, actually just even without the abbreviation, doctor, doctors, we should recognize that those are the same word. And then the last thing we will do is we will convert to a list split at white space. Split at white space. Awesome. All right, so that's tokenization, and then I'll tell you about something called a bag of words representation. Now that the term bag of words can actually represent different vectorization techniques. It's not, this often happens in machine learning. Very often you will hear a term and it is actually not formally mathematically defined. It is sort of defined in the sense that usually when people use it, they mean this thing or that thing, like one of two or three different things. I'll give you my favorite example, the word neural network. Neural network. A neural network is not formally defined in one consistent way across papers and textbooks. Typically, a neural network refers to a very certain type of mathematical function that can be expressed in a certain way using linear algebra and a small set of well-known functions. These are called activation functions. But even though that is the typical definition, there are so many different edge cases that some people would probably say it count as a neural network and other people say don't count, that I don't consider it to be a well-defined term at this point in time. So bag of words is one of these, and usually with bag of words, there are two different things. One is a binary bag of words, so which I would call a set of words. And then the other one would be sort of like a frequency. In NLP, the word frequency means counting. It does not mean frequency as in physics, where there's some kind of periodic behavior and you're measuring how often that happens. It's actually always a count, an integer positive count, frequency, or a multiset. If you haven't heard the word multiset before, a multiset in math is a set where there's no order to the elements, but a multiset, unlike traditional sets, a multiset includes the count of each item in the set. In Python, there's a class called a counter, which basically maps whatever your keys are to a non-negative integer. And that is one way to record a multiset in Python. So if you're used to counters in Python, then that is a multiset. Okay, so bag of words, basically, in order to use a bag of words, typically you choose a vocabulary, which is going to be a set or a list. In this case, I'll call that a list of tokens. And then given a document, you map that document to a vector based on how many times the token appeared in the document. The token was in the document. Let me try to explain that. So think of the vocabulary as a list of tokens. Then if there were only 5 tokens, then the vector would be something like, in the binary case, it would be like 0, 1, 1, 0, 0. And that would simply mean that the second and third words in your vocabulary were in your document, and the first, fourth, and fifth tokens in your vocabulary were not in your document. Okay, so bag of words is a type of technique usually applied after tokenization that will allow you to convert documents into vectors. One of the nice things about the bag of words technique is that the output is always a fixed length vector and the coordinates are consistent in what they mean. So I could have a series of tweets and I could have a series of books, and I'll map them to the same mathematical space with the bag of words model. All right, that is not Tf-Idf, but Tf-Idf is going to be similar in the sense that each coordinate in Tf-Idf will correspond to a single term in your vocabulary. So let's actually define Tf-Idf. So let's say we have a document D, document D, and a term T. So document, as a programmer, you think of that as a string with natural language data, such as English or Chinese, whatever your language is. And then a term is the same as a token, usually a word, but it could be, for example, a phrase or a subword. Topics I've skipped. If you like diving deep into things, you could look into something called stemming or lemmatization. I won't get into these, but I'll tell you what they do. These are ways to address the fact that in English and many languages, conjugation or inflection changes will change the spelling of a word, but it's essentially the same word. So for example, I often go running, or sometimes I run, or yesterday I ran. Those are all spelled differently, so in a strict vocabulary sense, they will all be seen as different tokens. But semantically, I'm talking about something very similar. So stemming or lemmatization are two different, very closely related approaches to try to solve that problem, where we recognize that these are basically the same word. All right, but I'm not going to get into that any more than that. Let's see. So Tf-Idf again, term frequency, inverse document frequency. The term frequency given a document D and a term T is going to be the number of times term T is in doc D. All right, so it's it's just the count. It's pretty simple. The document frequency doesn't depend on a document. Document frequency only depends on a word, and this is there are different ways of defining this. Again, this is one of these areas where things are a little inconsistent. But basically what we'll do is we'll look at the number of documents that have term T in it. Okay, and then I'm going to divide that through by the total number of documents. Okay, so it's going to be a number between 0 and 1. And the Tf-Idf vectorization, or the Tf-Idf vector of a doc, is going to be a vector. So let's say this is the ith coordinate of that vector. So I'm not writing all the coordinates. I'm just going to write one example coordinate to show you the idea. The ith coordinate here is for the term or the word T sub I. Okay, so for example, that might be the word pizza. So the actual value here is going to be the term frequency. So this is, we have a doc D, the term frequency of that document containing the word pizza, TI, divided by the document frequency for TI. Now there's a lot of things that can go wrong or right here, and one of the most obvious things that can go wrong is you could divide by 0. Sometimes people just put a +1 at the bottom because then you avoid dividing by 0, but then it feels sort of morally wrong to prevent this from being a 1. So often when people put a +1 in the bottom, they also put a +1 in the top, but it's optional. The +1 in the top is optional. And then sometimes people put logs here. So they might write log of this whole thing, or they might write log of just the top or just the bottom or both of them separately. So there's a little bit of anarchy, in my opinion. Why would you want to throw logs in there? Basically, logs are useful when you have spiky values. If you looked at the histogram of the Tf-Idf scores without a log, the histogram might look something like this, where, or I won't even draw a histogram, but I'll just plot values. You might have a bunch of values here, and then you might have a value over here that's extremely high, and that value will dominate too much. You want to sort of you want to try to get like a uniform histogram if you can, and logs tend to smooth out weirdly shaped distributions of numbers. There's not really a formal basis for exactly what the best formula of Tf-Idf is. It's a collection of formulas that have been shown to work well in practice. Conceptually, the term frequency is saying how much is this document about this word. If it only mentions the word once, kind of. If it mentions that word 20 times, probably a lot. And then document frequency is trying to say, oh, okay, if it's the word the, we don't actually care about the word the. We're going to basically minimize the score of the word the if we have a huge corpus, a set of 1 million documents, and this is the only document that has that word in it. Probably it's a typo, right? But pretend it's actually just a very niche topic. Then we'll actually emphasize the score of that word for this document because there's something really special and meaningful about that word. That's the intuition behind Tf-Idf. Okay. Next, I'm going to talk about logistic regression, and what I'll do is I will give an introduction to logistic regression using GoodNotes. This is the app I'm using, and after that, I'll give you an example. So far, the entire video is all writing notes, but I do plan to include some examples after this. Okay, so logistic regression. So logistic regression is a binary classification approach. All right, it comes with its own training loss function, its own way of training the model, and the simplest part of it is probably how it actually predicts points. So, all right, so prediction is easier. So pretend like we have already trained a logistic regression model. I'll show you how we actually how we map weights to an actual prediction value. So we have a trained vector of weights. So I'll use the word W for weights. And let's pretend like it's a length 3 vector, which is a very simple case. Right? And then we have some kind of input vector, which we've never seen before, but this is our data, our unlabeled data. Input vector X. So this is unlabeled data. It might be new. I'll pretend like it's new for this example. X1, X2, X3. And then the actual prediction, or really, I'll start with the confidence score. The confidence score, which is often interpreted as a probability, although I would not define it as a probability. I would just say that's simply how people tend to think about it. The confidence score is going to be, I'm going to write this in a few different ways. I'll use a function sigma, which I will define in a minute. Sigma of the dot product between X and W. Okay, that's the confidence score. So let me define the terms here. Sigma of X, this is called the sigmoid function, is 1 over 1 plus e to the negative x. And if we were to map this function out, it's a beautiful function. It's monotonic. That means it's always increasing or always decreasing. In this case, it's always increasing. It's always in the range 0 to 1, exclusive. It goes through the point 0, comma half. Okay, so the midpoint is at 0, input 0. If we were to lower it down, it would be an odd function, meaning it's symmetric. And it has nice calculus properties as well. So this is called the logistic function. And this is the reason it's called logistic regression. Actually, the name logistic regression is very interesting. It is, the word regression is super weird in statistics. So the word regression in statistics means the output of your model, in machine learning, by the way. In machine learning, the word regression means the output of your model is a floating point number, not a classifier output. Okay, now if you're a very smart person, you'll probably be saying, wait a minute, isn't this a binary classifier? Excellent point. You're right. It's weird that the word regression is used for logistic regression because it is not a regression model. Okay, so it is weird. It's a misnomer. The reason the word regression is used here is that it is extremely similar to linear regression. I mean, under the covers, it's basically linear regression, and then someone stuck a logistic function on top of it. So the name kind of makes sense, even though it's a little messed up. Okay, and then the actual classification, the actual prediction here, as I mentioned before, the actual prediction is rounding the value of the confidence score. Okay, So that is how logistic regression, how it actually predicts values. And then there's something interesting about how it trains. But before we get to training, I want to try to give you a little bit of intuition. Logistic regression, intuition. Okay, so I'm going to draw two different views of line fitting. So this is line of best fit. All right, so obviously this data has a line that goes basically through it. So we're going to find that line. Boop. Good job. Whatever that statistical model was, it worked well. Now let's pretend, actually I'm going to try to draw something 3D. So please use your generous imagination to view this as a three-dimensional set of axes. And it's going to get even harder because somehow we have to imagine this quadrilateral that I've drawn as a sort of like a piece of paper floating in space. And let's pretend like there are these points that are very close to it in space. So these are both, so this is a hyperplane of best fit. A hyperplane is basically it's sort of the n-dimensional version of a plane. So in 2 dimensions, this is 2D, a hyperplane is a line. In 3D, a hyperplane is a plane, like a flat surface. In 4D, a hyperplane is a 3-dimensional surface, but it's actually kind of flat in 4D. 3D is kind of flat in 4D. And so in general, hyperplane is has one less dimension than the space it is in, and a hyperplane is always flat in some sense. It's a linear or affine subspace. This would make more sense if we studied linear algebra. I'm worried about getting too advanced into arbitrary dimensions just yet, so I'm not going to go there. Now what I can do here is I can apply the logistic function. The reason they use the Greek character sigma for the name is that it is sometimes called a sigmoid function. So if you think about it, like the letter S, if you sort of write it like this, is kind of the shape of the logistic function. Okay, so that's why we use the Greek letter sigma. Sigmoid. Okay, so let's apply the sigmoid function here, and it's going to give us something that looks like, I wonder if I can move this line. Oh, I can. Look at that. That was fun. Yeah. Okay, so there's a few outliers. The reason I've moved this line is because I want to draw a more interesting example. The point where it crosses 0 is about here. So this is about where we're going to hit 0.5. And then we're going to go up from here. So all of a sudden, instead of having a line, we have a sigmoid. And then something similar happens when I apply the sigmoid curve to 3 dimensions. And actually, this is the most interesting part of this picture. Now, this is very hard to draw. What I'm going to try to draw is a flat surface that has kind of a step up, or like a kind of like a waterfall up, because it's not an abrupt cutoff. It's sort of a smooth transition to a higher plane. All right. So if you can imagine sort of a waterfall here, this is all part of this surface. And the interesting thing is this previous hyperplane could go up to positive infinity or negative infinity in terms of its height values. But now, after changing things by applying the sigmoid function to it, it's in the range 0 to 1. So it's now bounded in terms of the height values. And the final formula here, if this is z, x, and y are my axes, the final formula here, I'll use a different color to make it easier to see this, is going to be z is equal to sigmoid, the logistic function of something times x plus something times y, and then we'll often have what's called a bias term, which is basically a constant you add on to the end of that list. So this is an example of a logistic function, the same type of function that is found in logistic regression. All right, now the reason this last picture is interesting is that this can kind of give us the intuition to show why this type of equation is useful for classifying data. So what I'm going to end up doing here is I'm drawing a bunch of pluses. So let's say I have a bunch of pluses over here that should be classified as ones. All right, and then let's suppose I have a bunch of minuses, which I'm going to draw over here, which should be classified as zeros. Then what I can think of myself as doing is basically finding the values. Let me write it like this. Find A, B, and C, these values, A, B, and C, so that Z of this Z, I'll call this Z hat. Well, should I call it Z hat? I'll just call it Z. So Z of XY is kind of close to the true label of each point, of the known training points. And I didn't tell you how to find those A, B, and C, but I'm telling you when you train, you pick these values, A, B, and C, and when you're done, you have a function, you have a fixed function, which basically is choosing a cutoff. Like if I were to draw an overhead view of this, so let me erase some stuff here. Okay. So if we were to draw an overhead view of this, then I'd have like X and Y, and then I've got my pluses. Where are my pluses? Which quadrant are my pluses? My pluses are sort of like, they look to me like they're positive Y. I'm just going to draw the pluses up here, and then I'll draw a bunch of minuses down here. And then that sort of magenta decision curve ends up being here, and this is basically sort of capturing the cutoff line where anything here is a yes, anything on the other side is a no, and this is called a decision boundary, which kind of makes sense. So that's some intuition behind logistic regression. I think I'm actually going to save the loss function discussion for another video because this video is already pretty long, right? So I'm going to stop right here, and in part 2 video I will go through a Jupyter notebook and we'll take a look at some like very quick example runs of these ideas. So if this is your first time seeing this, there was a lot of content in this video. I wish I gave more examples. I will give you examples, so maybe look at the second video, and if you're like me, you would actually probably enjoy watching them again. For me, if I'm learning a completely new concept, I like to have a little bit of redundancy in learning. So I like to watch one video or read one good source, try an example, and maybe go to the same source again, and then everything makes sense the second time. So I encourage you to keep that option in mind.